Hi, my name is Dr. Davies, and I'm one of the chemistry faculty here at FGCU. This week we're going to be doing an electronic experiment called the missing label experiment. The basic setup for this is that these 5 vials that you see sitting in front of us have been sitting on a shelf. We are out for the weekend and, I guess the air conditioning shut down, room got very hot, it got humid, the labels all fell off. The air conditioner kicked back on and blew the labels around, so we still have the 5 light labels, we still know what the 5 substances are, we just don't know which ones are which anymore. And in all these cases, the substances are dissolved in water. So that's a useful piece of information for us to start with. Now what we can do to try to identify these is we can look at what happens if we were to mix them together, since we do know what the substances are, and we can try to identify things based off of chemical reactions. Now, looking at some of those chemical changes that could be occurring, when this reaction happens, remember, this is happening at the micro scale between individual molecules. That said, we don't live at the micro scale, we live at the macro scale. So we have to look at the larger scale changes that we can actually observe. So you've probably been taught in elementary school or middle school that when a reaction happens, you'll see these physical changes. We also know now that it's a little more subtle than that. Just because you have a color change doesn't mean a chemical reaction really happened. So there's a little bit of a disconnect between the macro scale observation and the micro scale, but it's still a pretty good indicator when something does happen. So looking at some of those possibilities, we have the ability to see a change in color. That would be an indication that a chemical reaction may have occurred. We can see the appearance of a precipitate, in other words, a solid. Now these crystals of the solid or particles of the solid may be very small and make the solution look cloudy like milk, or they could be fairly large and they settle out as big grains of almost sand-sized crystals, maybe even bigger, right? Typically this will also have an accompanying color change because we change the state of matter, and that often will result in some sort of a color change. We may have the precipitate just turn out to be a milky white color. It could be black. It could be any of the vivid or dull colors that you might expect from any sort of reaction. Remember, all of the particles that you see in paint probably came from some sort of reaction that was a precipitation and gave you those tiny particles sitting in the paint can. So we can definitely have a variety of colors when it comes to the precipitates. We can also have the formation of gas bubbles, and they may be very tiny and they may look like a cloudy substance, kind of like a precipitate. Big difference is if you let it sit for a little while, the gas bubbles will eventually leave the solution, whereas the precipitate is just going to settle out as grit at the bottom of whatever you're doing your measurement in. But they can look very similar early on. Now, a fourth possibility might be the emission of light. An example of that would be setting something on fire, right? We could have a change in the odor of the solution, and we could have a change in temperature. The thing is, those last two are going to be really hard for us to have happen and observe when we're working electronically. We're just not going to be able to see the temperature change or a change in odor of the solution. And in fact, if we were doing this in the lab, we'd still have a hard time seeing those things because we're typically going to work in very small volumes, a couple of drops mixed with a few drops of the other chemical. So there's probably not going to be a lot of the ammonia smell, for example, if we were to generate ammonia. So we may not notice the emission of odor or a change in temperature. We would probably notice emission of light, but that's not going to be one of the ones we focus in on today. We're going to focus on these 3 chemical changes as something we are looking for in the experiment we've set up online. So looking at those, we can think through what kind of changes might matter. And for that, let's remind ourselves a little bit about how precipitation works and how gas-forming reactions work. Now, going to the idea of a color change, we could have something like an acid-base indicator as well, and that's going to be something where the molecule changes color depending on which of the 2 forms it's in. That would be one way we could have a color change. We could have a color change because we formed a different phase of matter. So something that was dissolved turns solid. A good example of that is when you look at the powder in Kool-Aid, it's one color. When you dissolve it, it's a different color. Now notice that's not a chemical reaction. Sometimes just changing your phase of matter can give you a color change, but it could also be from a reaction. We have to look a little more deeply to know. And so we're going to focus on the color changes that do happen from chemical reactions. Now, we're not going to worry about acid-base indicators, like I said. We can have phase changes, so something that's aqueous, dissolved in water, becoming into a solid, or turning into a gas. It could even possibly turn into a different liquid that's immiscible. We don't see that really commonly, and it's not going to be something we have to worry about in today's work. But I'll point out we could have some sort of like a liquid fat sort of thing mixed in with an aqueous solution, and that would still give us a color change, the cloudiness that you might expect, right? We're not going to have to worry about that one. We're mostly going to be focused on the idea of precipitation. We're going to have something that was aqueous react and form a solid, or gas generating reactions where the aqueous reactants turn into something gas phase. So that's really where we're going to focus for these experiments. We'll need to use our precipitation tables. You can find those in table 9.1 in your textbook. We're also going to look at the gas generating reactions on table 9.3. Now going into those a bit more deeply, this is our solubility table. Now I've added one extra species versus what we see in our textbook, and it's going to be our ClO4 single minus. Now you'll notice that these 4 ions, they typically are going to stay aqueous. They're just not going to precipitate out with anything. And so that's a really useful thing to notice. These are cations, are positive ions, that are generally going to stay soluble. So it doesn't matter what's paired up with it, it's going to be soluble. These ones are anions, same thing. These are the ones that are always going to be soluble. Or maybe I should put finger quotes saying always. They're generally soluble. You'll find some exceptions out there. Now you might say, well, wait a minute. If our goal is to do something about precipitation, these aren't going to precipitate. They're always going to stay aqueous. How are those helpful to us? Well, they're really useful because those things start out soluble, right? So anything bound together like sodium nitrate, Na and NO3, that's definitely going to be soluble, right? You put that into water, that means that that has immediately popped apart into sodium ions and nitrate ions. Now when I mix something else into there, if these pair up with something different and they can actually precipitate or form a gas, that's when it's going to be reacting. So those first 2 categories are really useful as host ions, because I can't just have sulfate ion sitting there by itself, right? It's a double minus charge. I have to have some plus charges sitting there with it to keep it charge neutral. So we can have those potassium ions or sodium ions just sitting around in the solution. They've dissolved, they're sitting there waiting, nothing else is happening. Now suppose that I mix in a barium nitrate solution. Well, barium nitrate will be soluble. Sulfate's always soluble, except when it pairs up. Notice that the exception did something useful. The exceptions, when you have barium ion and sulfate ion, those pairing up become insoluble. So that's what we're using. We're using the exceptions to make all the things happen. So when you go to memorize these for the lecture set of class, don't get caught up saying, oh, I'll memorize the big rules, because the exceptions probably don't matter. It's very much the opposite. The exceptions are where we actually make use of solubility to do things. So make sure that you pay very careful attention to both columns when you're learning these. Now, like I said, we're going to solve for what our ions are for both species that we're going to mix. So if I have NaCl, sodium chloride, and I have, just picking something else, how about NaOH? Na and OH minus. Those are going to pop apart. Notice that OH minus is usually insoluble unless it's paired up with Na. So that will be soluble. I'll have Na ion, OH ion. So sodium ion and hydroxide, right? I will also have Na positive, so that'll be sodium ion. And I'll have my Cl minus that I just mentioned, sitting in solution. Now we switch the partners. We say, okay, let's take my Na and I'll pair it up with my OH. Neither one of those are going to precipitate. Nothing happens. And we're just going to switch the partners and see if there's a precipitation. That's how we're going to use solubility. Also remind us that any of these things that are dissolved are going to be called electrolytes. Whether they're just regular metals, anions, whatever, or even if it's an H plus or an OH minus, the acids and the bases. Those are still going to be electrolytes. So even when it's a strong acid or strong base or a weak acid or weak base, still considered an electrolyte, as are these salts. Now what about our other category, our gas generating reactions? Well, you can see these are gas evolving or gas generating reactions. They form a gas as a product. And we've all seen one of these before. We've all seen this line right here. Although we probably used vinegar or citric acid or something like that. We mixed it with the baking soda, and out of that we got some water forming. We formed carbon dioxide that bubbled out of it, and we had some sodium chloride that stayed dissolved. Gas generating reaction. We're going to see small bubbles coming out of that if we mix typically an acid and a carbonate, but there's some other examples as well. Like we can form ammonium ion. Take the ammonium ion and form ammonia. Quick point, you know how they tell you not to mix strong bases with ammonia? That's one of the reasons. We don't want to be forming tons of ammonia gas. You can also form some other nasty side products. So be careful when you're doing these sort of things at home, especially if you're talking about cleaning supplies. You could start forming chlorine gases and things like that as well. Gas evolving reactions aren't always friendly. We're going to stick with the ones that are more obvious and aren't so bad. The worst that you have in this list is probably the sulfite creating SO2. That's kind of that stink bomb smell that you smell when you set off a stink bomb. The sulfide groups and the sulfur dioxides. Those are pretty nasty. They're in some of our smog and other sorts of irritants that we have in the gas phase. And of course, ammonia is not great to be breathing real strong either. Okay, so those are going to be the reactions that we have as a possibility. Now from here, let's switch over to the actual simulation. This is the simulation window. You'll find the link posted up in Canvas. You'll also see it listed up here on the top if you wanted to just type it directly. Now here's how this operates. First we start out taking some knowns. So we're going to take some solutions that are the same as we found sitting there marked on our labels. And we're going to say, neat, let's figure out what's going to happen when we mix them together. Because if I recognize a reaction's product, I can then look for that in my unknowns and identify things based on that. Now here's the basic way that you're going to manipulate this. You're going to grab one of these pipettes. These are just those little plastic squeeze bulb pipettes we have in our lab. You click on it once, then you click down here, and it'll dispense into that cell. If you want to move to a different cell, click, dispense. So you hear I'm doing 2 clicks. Click, dispense. So I'm just going to go ahead and set them up in all the columns. And it's going to try to auto-place them once in a while for me. Oops. And I'm just going to tell it where I want it. So I'm going to go down the entire column and put some into each column. So first I'm going to do that for each of these 5 rows, each of the 5 columns. Then I'll worry about adding for the rows. Oh. Sometimes you have to click more than once, but it'll work. So we're just going to go through and add through the columns. I'm not going to worry about finishing going across each of these columns, just for brevity's sake. Next up, what we can do is we can take this solution, in this case HNO3, click that, and I'm just going to come across the row. Now notice that that has some bubbles forming. I want to mark that down. Now there is a tool over here where you can record your observations, and it explains that down here. Personally, I would recommend you just do this on pen and paper. That way you've got it sitting in front of you and it's easy to refer back to as you go forward. Then we can just come across and see if anything happens in any of these other cells. I'd recommend making a little grid on your paper before you start doing this, so that you can quickly record things when you do observe something happening. You can just write down bubbles, precipitate, white, black, gray, whatever color it ends up being, and keep track of it that way. And so that's all you need to do. You're going to go through all 5 of these with the columns, then you're going to mix them in the rows. You might even say to yourself, wait a minute, I don't expect much to happen if I mix K2CO3 with more K2CO3. Congratulations, you've correctly recognized that this whole diagonal is going to have nothing happen, right? You're just mixing the same substance with itself. We also don't have to do the bottom of this triangle, I guess, because notice that here if I'm mixing HNO3 and K2CO3 on this one, above the diagonal I'm also going to be mixing the same things over here. You can recognize that and save yourself a little bit of time. Personally though, I would just go ahead and do it. You're only mixing a total of 25 cells instead of doing 12. It's not going to save you much time. In fact, it might even be harder for you to notice or to keep track of what you've been doing. So I recommend you just go ahead and do the entire grid rather than focusing on just doing north of diagonal, if that made sense. If not, just focus on doing them all. Once you've done this and you've recorded observations for all of these mixtures where you know what you're mixing, you're going to go over here and click the unknowns. And I'll also point out this list and this order is going to randomize slightly from time to time. Let me just show you that by hitting F5 to refresh it. You'll notice these just changed a little bit. The positions are all changing each time. I'm getting different substances. So we will see some changes when we do this. But when you're set here and you don't refresh, you can go to unknowns. I'm just going to keep the same set of unknowns. It's just that now you only know that it's bottle 1, 2, 3, 4, and 5. So once again, we're just going to go ahead and let's just put substance 1 in each of these columns. And then we rinse and repeat for all of those. Then we put 1 across for all of these. Then we come and we do the acrosses. So I'm going to just grab number 2 just to demonstrate this a little bit faster. So I'll mix there, and then I'll just come across and mix all of these. Record all your observations. Now if I spot the one that bubbled, and there was only one that bubbled, I now know which one it is. You're going to go through it back and forth until you figure it out like that. So that's the basic approach you're going to use for this one. If you have any questions, make sure you get a hold of whoever your lab instructor is, and we can get back to you with some answers. Of course, if you want to start in on this a little bit early, that's always an option. Just make sure you get a hold of us with any questions. With that, I hope you enjoy this experiment. It's actually kind of a fun one. It's sort of a logic puzzle. It's even more fun in person, in my opinion, but online's not too shabby. Thanks for listening, and hope things go well for you.